So, in the previous video, we talked about what is thermodynamics, broadly speaking, how do we work with thermodynamics. We said we work with laws, and we talked about why these are laws and what are the assumptions behind these laws and so on. In this video, we are going to be talking about a very important part of this science of thermodynamics, and that is the units. Measures, right, and standards. So, you might say I already know units, what's the big deal, right. So, I have already know that there are units for length, units for mass, units for everything, right. So, what's the real need to again learn or look at units and standards. It is very important because as scientists and engineers, we must be precise in what we say, right. We must be exact. We must convey exactly what we mean and not anything else, right. And this is particularly important for you because you have come from the JEE system, right, and the JEE system unfortunately is no longer written answers, it is only multiple choice. Right. And so, there is not much emphasis on things that cannot be tested using multiple choice questions. And so, therefore, you might not have paid attention to the right way of doing units and dimensions, right, and standards. Right. So, again there are some fundamental units. What are those fundamental units? Length, then time, mass, what else? Temperature, and then light intensity, yes. And quantity of matter. Right, and we know that these are the fundamental units or the primary units, and everything else is a derived unit or a is derived, right. So, what are some of the derived units? Examples: work, energy, force, current, what else?
You can say power. Power.
Power, yes.
Acceleration.
Velocity, acceleration. And there are so many others, right. Now, what is the SI unit for length? Meter, right. So, this is meter. For time? Second, and for mass?
Kg.
So, kg, right. For temperature?
Kelvin.
Kelvin. For light intensity?
Lumens. Oh, candela.
Luminous intensity, candela, right. And then quantity of matter?
Mole.
Mole, right. Right. Notice that I have to write meters. There is only one way of writing meters, right. So, in the open literature, even in some scientific, so called semi-scientific literature, you will find on websites, you will find meter written in different fashion, right. So, you will find that people write meters any way they want. So, people write meters like this, right. So, when they say 10 meters, they sometimes write like this, right. Sometimes they write 10 like that, and sometimes they write right, and well, sometimes you may understand based on the context what they actually mean, right, but sometimes you also lead to confusion. And so, as engineers, we must write things precisely, especially units. We cannot afford to have confusion in how to write units, because then we will never get anywhere. Okay. So, it is important to know that 10 meters, if you have, let us say the length of this room is 10 meters, okay, there is only one way to write this, okay, and that is 10 m. Notice that the m is simple case, not the caps, right, and there is no full stop at the end of m, right. So, all of these are required. You cannot write this or this or this or this, right. All of these are incorrect. Right. And similarly, for time, you will see people write 2.5 seconds. You will see people write like this. Okay. You will see otherwise people write, or they write something like that, right. And again, all of these are wrong. There is only one way to write 2.5 seconds, and that is this, with a simple case s, not with a capital, right. So, similarly, people write temperature, right. As 100.5 Kelvin, right. What is the right way of writing this? You can write this as 100.5 Kelvin. Why is this a capital K and not a simple k?
Small k means kilo.
Small k means kilo, we will come to that, but why is it fundamental units? We are talking about units. We will talk about multipliers a little later. Okay. Small k is a multiplier, but as a unit, why is this a capital K and not a small k? So, for example, if I have a force, right, what is the unit of force? Newton.
That is a scientist
Unit of
name.
energy and work?
Joule.
Joule.
Yeah.
And unit of current?
Ampere.
Ampere. Power?
Watt.
Watt. Acceleration?
That is meter per second square.
Meter per second square. Velocity?
Meter per second.
Meter per second. Right? You notice a trend?
It's in Newton. Sorry, this is a scientist name.
Right. So, if it does not have to be a scientist, but yeah. So, the idea is that if it is named after a person, it needs the first letter of that unit need to be capitalized, right. So, we write 10 power 5 Pascal, right. So, that is Pascal. So, Pascal you write, there is only one way of writing Pascal, and that is with a capital P and a small a, right. And this is 10 power 5, which is the number of Pascals, right. You can also write it as right. So, you can also write the full form if you want to. Nobody does that, but if you want to, you can write it and it would be right, it would be correct to do that. So, I can also write this as the force equal to 7.3 Newton. So, this is correct, but if I try to be too smart and I write pascals like this is not correct. Okay. And if I write 7.3 newtons, this is not correct. 7.3 Newton, this is also not correct. Okay. So, the easiest way is to just write it as 7.3 N, right. So, it is important that we follow this convention, right, and pay attention whenever we are talking about units. And of course, if you have an equation, you know that all the terms in the equation should have the same units. You cannot add two quantities which have different units, right. It sounds very obvious, it sounds like something that you ought to know, but we do mistakes because we try to add or subtract things that are at different units. Now, we come to something called multipliers. What are multipliers? Multipliers are necessary because many of the physical quantities, they are not really intuitive when you talk about it in just the units. Like for example, 10 power 5 pascals is 1 bar, right. So, 1 bar is another unit of pressure, not the SI unit, but another commonly used unit and that is equal to 10 power 5 Pascal, right. And it's convenient to talk about bar. So, we sometimes use bar, but we also talk about, like for example, this is also equal to 100 times 10 power 3 Pascal. And so, I can write this as 100 kilopascal, right. So, this K here now becomes a multiplier to the Pascal. So, it is not Pascal, it is kilopascal, right. And again, kilopascal, there is only one way of writing kilopascal, K is small, P capital and A is simple case again, right. You cannot write it as KPA, this is not correct, right. So, what are some of these multipliers? So, 10 power 1, if you want to multiply it with 10, it becomes deci or d. So, for example, if I want to say 80 meters, I can also say 8 decimeters. No, that is not right. Is that right? No, that is not right. Yeah, deci is 0.1. So, this is deca, right? And deca is designated by capital D, small d.
I think it is small h.
Let me check. DA, deca, okay. So, it is not DECA, it is DEKA and it is DA. So, DAM, right, it would be decameters. It is rarely used, so let us not worry too much about it. 10 power 2 is has a name, is hecto and H. And 10 power 3 is starts when it really starts to matter, because this is rarely used, right. So, we do not worry too much about that. 10 power 3 is kilo, and the multiplier designation is K, the same K that I used in the 100 kilopascal, right, and the same K that we use when we say the distance between Ahmedabad and Mumbai is, let us say, 800 kilometers, right. So, we write 800 kilometers. So, this is the K that I am talking about. So, notice that there is no space between the K and the M, right, and there is also no space between the K and the Pascal, right. So, it is written just continuously. If you give a space, then it becomes something else. Okay. Then 10 power 6 is mega, and the designation is M. So, I can also write this, for example, as 0.1 MPa, M caps, P caps, A simple case. And 10 power 9 is giga, that is right. So, what do you know is giga?
Like gigabyte, our
gigabyte, yes, gigabyte is
memories,
GB, right? Yeah. Okay. What else do you know is giga? How much power does a power plant produce? A coal power plant which produces power
gigawatts,
typically in gigawatt, right? So, 1 gigawatt. So, power produced by a power plant is 1 gigawatt. G caps, W caps. W because it is from watt, named after watt, and giga because it is 10 power 9 watts, and so that is 1 gigawatt. Some wind turbines are rated at 0.5 gigawatts or 1 gigawatt. Okay. Is that clear? Any questions? All right. And 10 power 12 is tera. So, you might have heard of teraflops. For supercomputers, they are rated as teraflops.
laptops also 1 TB, 2 TB.
Right. So, terabytes, yes. So, this is how much we use. Beyond that, there are other multipliers that we do not use that much. So, we will not worry too much about it. And then we have we also have smaller units. So, for example, if we are dealing with the energy conversion that happens inside a battery electrode, for example. So, then we have got to talk about millimeters and microns and nanometers, right. So, we also have to have multipliers for less than 1. So, 10 power 1 is 0.1 and that is deci, and the multiplier is d. 10 power minus 3 is milli, and that is m. 10 power minus 6 is micro, and that is mu, the Greek letter mu, right. So, when I say the thickness of a membrane is 50 microns, so what I mean is that the thickness of the membrane, so let us say the membrane is 50 microns thick, so I designate as 50 micrometers. So, it is 50 times 10 power minus 6th of a meter, right. And then we have 10 power minus 9, which is nano, right. So, a lot of things we hear these days: nanotech, nanotechnology, nanosensors, nano devices, nanotechnology, nanocatalysts, and so on. So, those are all at the scale of 10 power minus 9 meters, and that is why we need another multiplier. There is 10 power minus 12. I'm not sure what it is called.
picometer.
Pico, okay. So, pico, and this is P. So, sometimes you are dealing with time scales of the order of 10 to the minus 12 seconds, and so you can say delta t is 5.6 picoseconds. So, that means it is 5.6 times 10 to the negative 12 seconds, right. Okay. So, any questions? Okay. So, I would like you to read this section in the textbook that is called right. Okay. And we will continue in the next lecture.